Voices of the Satellites, recordings of the radio signals from man's first 5 space travelers. This is Professor Benham in the laboratories at Haverford College, bringing you the sound of man's first satellite. On October 4th, 1957, Russian scientists from somewhere in Russia fired the rocket that put the first artificial satellite into an orbit going around the world once in about 96 minutes. Man's first artificial satellite is called Sputnik, Russian for traveler. After Sputnik had made several trips around the world, scientists were able to establish its orbit. It turns out that the orbit carries the satellite to a maximum distance of approximately 600 miles from the Earth's surface and a minimum distance of 150 miles. The orbit is inclined to the equatorial plane of the Earth at an angle of about 65 degrees. The speed at which Sputnik has to travel in order to stay in an orbit like that is about 18,000 miles an hour, 5 miles a second. Powered telescope, and only when it is in just the right position relative to the Sun. While the 22-inch diameter satellite itself is not visible with the naked eye, the third stage rocket, which put it up there and which is also going around the Earth, is visible with the naked eye when it is in just the right position. However, the satellite has a radio transmitter in it, which means that the signals from the transmitter can be picked up any time that the satellite comes within 1,500 miles of the receiver. This happens 6 times a day, 3 times in the morning and 3 times at night. The transmitter is sending on a frequency of 20.005 megacycles. Let us tune in Sputnik again on our communication type receiver that we have here in the laboratory and listen to Sputnik as it was going approximately overhead about 400 miles up at 7:39 p.m. Eastern Standard Time, October 21st, 1957. Note that the signal is steady now instead of beeping. This is because the beeping mechanism failed after several days of operation. Valuable information can be obtained from this transmitted signal from the satellite to give us information about the position and distance of the satellite from the receiver. This is done by a very careful study of the frequency through a phenomenon known as the Doppler Effect, which is the change in frequency as the satellite goes by. Suppose we illustrate this with an effect with which everyone is familiar. If you are standing by a highway and a car is approaching blowing its horn, as the car goes by, there is a sudden drop in pitch. Listen. When the car passed the microphone, it was about 5 feet away and traveling at 60 miles an hour, which makes the pitch change very suddenly. On the other hand, the satellite is about 400 miles away when it goes overhead and traveling at 18,000 miles an hour, which makes the pitch take about 1.5 minutes to change. Remember that the further away a moving object is, the slower it seems to be traveling. Let us tune in on the satellite as it approaches from the southwest. It will travel overhead at about 400 miles altitude. Remember that the satellite travels about 450 miles during this 1.5 minutes. Now the pitch is beginning to change. Now the pitch is changing most rapidly, which means that the satellite is about overhead. You will notice now that the pitch is quite low, which means that the satellite is beginning to go away from us. You will notice that the pitch flutters a little bit in volume. This is due to variations in the ionosphere. Now the pitch is no longer changing, which means that the satellite has passed overhead and is going away from us to the northeast. In order to make this change in pitch more dramatic, let us listen to 3 seconds of the recording during the time that the satellite was approaching from the southwest, followed immediately by 3 seconds taken from that part of the recording when the satellite was going away to the northeast. From the complete change of pitch which was just demonstrated, the speed of the satellite can be calculated. And the distance to the satellite, when it is closest to the receiving station, can be determined from the change in pitch per second when it is changing most rapidly. Suppose we measure the speed of the satellite. Here in the laboratory we have an audio oscillator whose pitch can be changed by turning the knob. Now by comparing the satellite with this oscillator, we can determine the change. Now here is the pitch of the satellite signal as it approaches. Now let us compare this with the oscillator. Now they agree, and the oscillator dial can be read to see what the frequency is. Next we will find the pitch of the satellite signal as the satellite is going away. Here comes the oscillator for comparison. And now by reading the oscillator pitch, we can determine that frequency. Now from a knowledge of this change of pitch, with a little trigonometry, the actual speed of the satellite can be calculated at 18,000 miles per hour. To find the shortest distance between the satellite and the receiver is a bit more complicated because we have to determine the rate of change of pitch of the signal and find the point at which it is changing most rapidly. Then substitute this into a rather complicated formula. For example, the following recording is the 10-second period during which the pitch was changing most rapidly. Man's first artificial moon is a ball 22 inches in diameter containing radio transmitters, antennas, and batteries for about 3 weeks' operation. The entire weight is about 184 pounds. As we have already pointed out, the rocket that put the Sputnik into the orbit had a third stage which went into orbit also, so that the two pieces were going around together in the beginning. But every time that the satellite and its casing came down to the low part of its orbit where atmospheric friction could be effective, they would be slowed down. However, the rocket casing, being much larger and much more area than the spherical ball, would experience a good deal more friction. Consequently, the rocket casing would not be expected to stay up as long as the satellite itself. Indeed, this turned out to be the case. The rocket casing disintegrated and came down in the early part of December 1957, while the satellite itself continued for another month and finally came to extinction in the early part of January. Before this happened, however, the world was introduced to the next chapter in the saga of man's probe into outer space. On November 3rd, 1957, Russian scientists launched the rocket that carried Sputnik II into an orbit. The signal that you are now listening to was sent down by a radio transmitter in Sputnik II that was very similar to that in Sputnik I. From this signal, we can deduce the distance and the speed just as we could in the other case. However, there is a vast difference between this satellite and the first one. Well, for one thing, the weight was 1,100 pounds instead of 184 pounds. This in itself staggered the imagination of scientists, who thought even the 184 pounds of Sputnik I was large. Then, too, the orbit was quite different. The maximum distance was 1,100 miles,
and the minimum distance about 200 miles. The satellite traveled in pretty much the same direction as the first one did, which indicated that it was launched from approximately the same place. But these statistics, surprising as they are, were not what made Sputnik #2 so surprising. We were all amazed to learn that Sputnik #2 carried the first living thing into outer space. As a passenger, in a special chamber built into the satellite frame, was Laika, a curly-haired dog who had been especially trained for this flight. Especially trained in the sense that he had lived in a similar chamber on the surface of the Earth, under conditions exactly like those that he would experience in the satellite, except for one thing, and that is the lack of gravity. There is no way to do away with gravity on the surface of the Earth, but in the satellite that is spinning in an orbit where gravitational pull is equalized by centrifugal force, Laika, as well as all other parts of the satellite, would be weightless. Imagine living under conditions in which if you turned over a glass of water, it wouldn't run out. Or if you lifted your hand to scratch your ear, you would be likely to box it severely. Now, of course, the Russian scientists wanted to find out as much as they could about what happened to Laika up there in the satellite. They had the chamber equipped with the necessary food and oxygen to keep Laika alive, but they wanted to find out what happened to the circulation, for example. So they attached a small special microphone near Laika's heart and connected the microphone to an amplifier, which then was connected to one of the transmitters that was located in the satellite. On November 6th, after Laika had been up there for 3 days, all seemed to be going well, and her heartbeat sounded like this. And the next day, it sounded like this. Perfectly peaceful and seeming at rest. One night, when we were looking for the signals from Sputnik II, an amusing thing happened. There, right on the frequency of the satellite, was a weak, plaintive signal sending from somewhere far away in Morse code. And when we translated it, we found that it was saying, bow wow. It turned out later that someone in the South Pacific was exercising his sense of humor. Although the Russians were first to put a living creature into an orbit around the Earth, there is strong evidence to indicate that the equipment they used was developed at the Naval Development Center in Johnsville, Pennsylvania. Thus far, we have talked about and listened to 2 of man's first 5 satellites, Sputnik #1 and Sputnik #2. What the Americans were doing about this, meantime, will be told on the other side of Voices of the Satellites.
The first one is the beeping Sputnik #1. The next one is a recording of the Doppler Effect for Sputnik #1, recorded at 7:39 p.m. Eastern Daylight Saving Time, October 21st, 1958. following is a recording of the Russian Sputnik III, launched 2:41 a.m. Eastern Standard Time from somewhere in Russia on May 14, 1958. The following recording was made under rather interesting conditions. I predicted that at noon on that day, the satellite would make its first passage over the Philadelphia area, but I couldn't be here at that time, so I set the receiver and the recorder and a timer and went away and left it. And when I came back, I listened, and here is what I had. Next is the heartbeat of Laika, the dog, in Sputnik II, recorded on November 6, 1957. Fading was quite severe that night on account of Aurora Borealis display, so we have taken 10 good clear heartbeats, repeated it several times, and spliced them together. The splicing is not perfect so that the break in rhythm is obvious.